Good morning, students. In the previous class, I started with the chapter Language of Chemistry, and as you can see, it will continue in this class also. I'll start from the portion where I gave you that homework. I've given you certain homework or assignments. I hope you have practiced those things and you have listened to the lecture carefully, and after listening to that, I hope you are able to solve those numericals. Not very difficult. Those numericals are, and you haven't faced any sort of such difficulties that you were unable to solve it. But still, if you are unable to solve it, I'll start with those questions in this lecture, this class. Okay. And let me tell you before starting that if you're having your any new exercise books, you can do it over there. It can be ruled or it can be Interleaf. If you're having using Interleaf exercise books or copies, you can write on both sides. If you're having ruled exercise books or copies, you can definitely write on the both sides. The next thing is it's regarding submission. Just do your work and follow the lectures properly. If you're having books, it's fine. If you're not having, the study materials will be provided to you. You can go through those study materials and you can clear your doubts. Until and unless you don't panic right now. The materials which the teachers will provide, I think that's enough to go through the syllabus. And right now, whatever it's been going on, you don't just panic yourself that exams are not coming right now. It's just the beginning of the session. Go through the syllabus, rather the chapters and the lectures which are going. Syllabus that also will be provided to you in the due course of time, so you don't have to panic. Okay, just relax, listen to the lectures and understand the things, clear your doubts and concepts, and when the exams will come, definitely you will not face any sort of problems, and other problems, we are there to sort it out. Okay, so let's carry on. Now the homework, the first question given was percentage of oxygen in a sugar molecule. Percentage of oxygen in sugar molecule. For doing this one, we definitely want to have to know the molecular formula of sugar, and which is C12H22O11, which means 12 atoms of carbon, 22 atoms of oxygen, and 22 atoms of hydrogen and 11 atoms of oxygen. All right, so 12 atoms carbon, 22 atoms of hydrogen, and 11 atoms of oxygen. The molecular masses of carbon 12 AMU, hydrogen 1, and oxygen 16. And the molecular mass of sugar, it turns out to be 342, and similarly percentage of oxygen 176 by 342 gives 51.46. 176 AMU means 11 oxygen atoms, 16 AMU each, so 176 AMU. 51.46. The next question given, calculate the relative molecular mass of green vitriol and the percentage of oxygen present. Green vitriol molecular formula, it's hydrated ferrosulfate. Remember, FeSO4.7H2. Probably, if I'm not wrong, you have read this. You have read this formula in the previous class. Chapter was water. The section water of crystallization. So green vitriol, FeSO4.7H2O. The atomic mass of iron given, and you can ask that why the rest of the mass is not given. I will expect that along with the atomic numbers, in the previous class also I told you that along with the atomic numbers, memorize the atomic masses too. Memorize the atomic masses too, along with the atomic numbers. All right. So green vitriol, so its atomic mass is 56. Iron, it's having atomic mass 56. So the relative molecular mass of green vitriol turns out to be 278 AMU. If you notice that each and every calculation, the previous and this one and the previous one, each and every calculation, I'm writing 56 AMU plus 36 AMU. This AMU I'm writing constantly. That means, as I said, units are compulsory. In the previous class of the lecture also, I told you units are compulsory when you are calculating relative molecular mass. When you're calculating the molecular mass of a compound, you are giving the molecular mass of a compound. So it's not you're not writing mass number, you're writing mass. So when you're writing the mass, it is 276 AMU. So the atomic mass, the unit is 280 AMU. So the relative molecular, so the molecular mass is 278 AMU. So the molecular mass of green vitriol is 278 AMU. So 1 iron, 1 sulfur, followed by 4 oxygen atoms, followed by 7 water molecules. Okay. Now next we have to calculate the percentage of oxygen. Now that the thing is, when the question is about percentage of oxygen, that is, we are having oxygen with ferrous sulfate. We are also having oxygen with water molecules. So we have to consider the oxygen from both the sections. That is from ferrous sulfate as well as from water molecules. From ferrous sulfate, it's 64 AMU, and from water molecules, it is 112 AMU. So the contribution from ferrous sulfate, 4 oxygen atoms, 64 AMU. 1 molecule of water contains 1 atom of oxygen. 7 molecules of water will contain 7 oxygen atoms. So total is 7 oxygen atoms. So 7 multiplied 16, 112 AMU. So total contribution, the total mass of oxygen, 176 AMU. So percentage of oxygen, 176. Mass of oxygen, the mass of the molecule, multiply 100, so 63.31. I hope it's clear. The next coming, that is molecular formula of potassium ferrocyanide. Molecular formula of potassium ferrocyanide: calcium arsenate, aluminium phosphide, boric acid. Potassium ferrocyanide, K4, third bracket, Fe, Cn(6). Calcium arsenate, Ca3, AsO4 whole twice. Aluminium phosphide, Alp, boric acid, H3PO3. So if you're having the answers with you, you can verify. If you're not having, you can cross-check, or rather the solutions with you, if it's fine. If you're not having, the solutions are given. You can cross-check with your solutions. Okay. So coming to the next question, that is ammonium nitrate and calcium nitrate. Which of these two is a better fertilizer? Now for ammonium nitrate and calcium nitrate, we need to know the molecular formulas. Ammonium nitrate, NH4NO3, and calcium nitrate, CaNO3 whole twice. But for being a very good fertilizer, the amount of nitrogen present in a compound is very important. That's the main criteria for being, or rather a compound being a very good fertilizer. That's the basic criteria. That's the basic criteria that which is a very good fertilizer. That is the amount, how much amount of nitrogen present, right? So we need to calculate the percentage of nitrogen present in ammonium nitrate and calcium nitrate. Now, the percent for that, and by comparative studies, we can conclude which is a better fertilizer. The molecular mass of ammonium nitrate, it turns out to be 80 AMU, as you can see. 2 atoms of nitrogen, 4 atoms of hydrogen, and 3 atoms of oxygen. And you can see 80 AMU. Percentage of nitrogen present, it turns out to be 35%. Similarly, with respect to relative molecular mass of calcium nitrate, it turns out relative molecular mass of calcium nitrate, 1 atom of calcium and 2 atoms of nitrogen and 6 atoms of oxygen. Why 6? NO3 whole twice, that means 2 nitrates are present, 2 nitrate radicals or other ions are present. So 2 nitrate means 2 nitrogen atoms and 6 oxygen atoms. And hence, the molecular mass turns out to be 164 AMU. And thus, the percentage of nitrogen present is 17.07%. 17.07%. Thus, we can see that ammonium nitrate is having 35% of nitrogen content, whereas calcium nitrate is having 17%, merely 17, just the half amount of nitrogen, that is 17%. Okay, so the figures itself suggest that ammonium nitrate is a better fertilizer. The next question given, that was, what percentage of oxygen is present in magnesium sulfate? Now be very careful with this question. That is, magnesium, that question is, we have asked about the percentage of oxygen not in Epsom salt, but rather we have asked for the percentage of oxygen in magnesium sulfate only. So don't mix up. Okay, so do not mix up. Percentage of oxygen in magnesium sulfate of Epsom salt. That means first we have to know what is Epsom salt. Epsom salt is hydrated magnesium sulfate. So MgSO4.7H2O. This is Epsom salt. And what is magnesium sulfate? Is MgSO4. The question is, we have to calculate the percentage of oxygen related with magnesium sulfate. So what is the mass of oxygen present in magnesium sulfate? 64 AMU. 4 atoms of oxygen, 64 AMU. Molecular mass of hydrated magnesium sulfate, 246 AMU. 120 AMU plus this. So magnesium 24 AMU, sulfur 32 AMU, oxygen 4 oxygen atoms 64 AMU, so 220 AMU, 246. So percentage of oxygen present, that is molecular, or rather the mass of oxygen in magnesium sulfate divided by the molecular mass of Epsom salt, multiply by 100. Multiply by 100. And that turns out to be 64 AMU by 246 AMU into 100. That gives 26.002%. 26.02%. That is the percentage of oxygen present in magnesium sulfate of Epsom salt. All right? Okay. Now doing some classwork. Write the formulas of, the first formula is calcium silicate. Now, inorganic compounds are normally, generally, for inorganic compounds, the cation, the name is written first, and the anion name is written later. So the first word of a compound, that's the cation name, and the second word is the anion name. We know that one. So over here, calcium silicate, the cation is the calcium. And how do we represent symbolically calcium cation? Ca2+. And what will be its valency? 2. Anion, how symbolically we write anion or other silicate? SiO3, 2-. And the valency is 2. And we know that we will do the cross multiplication. Cross multiplication of what? Cross multiply the valencies of cation and the anion. That means that valency of cation will be multiplied with the calcium, and the valency of anion will be multiplied with the anion, and hence by cross multiplication we will write those valencies not at the top but as a subscript, which will give us the number of ions of individual cation and anion present in the particular compound. But there is a clause. The clause is, let's also remember that if the valencies are same, the cation and the anion valencies are same, then it cancels out each other. Right? It cancels out each other. So calcium silicate, if you cross multiply, then Ca2SiO3 whole twice, but this is absolutely wrong. This is not the correct formula. And hence, the correct is CaSiO3. And following this, there is a list of formulas. So, list coming later, but before coming to the list, there are various representations also. While writing formulas, I have noticed that there are various ways of writing subscripts. That is, Ca, there is a diagonal base, 3, or at the bottom of oxygen 3, or beside oxygen 3, or giving a space and writing a far distance away 3, or as if clinging to oxygen 3, or cubic. All these ways of writing formulas are absolutely wrong. Get this thing very clear. All these ways of writing formulas are absolutely wrong. When you're writing molecular formulas, write it clearly the way it has been mentioned, the way it has to be. Do not write in whatever manner you're feeling like. The correct way, it's that also being shown. CaSiO3, the subscript. You have to understand the difference between subscript and superscript and base values. At the base of this, at the bottom of this. No, it's not like that. Subscript, specifically subscript way, you have to write those values. So CaSiO3, this is the correct way of writing formulas. The rest of the ways are totally wrong. All right. The list of formulas include lead 2 oxalate, chromium phosphate, platinous chromate, magnesium perchlorate, zinc carbide, arsenic sulfide, manganese hypochlorite, lithium thiosulfate. All right, lithium thiosulfate. Now, regarding lead oxalate, that means the valency, lead is having 2 valencies. It's a variable valency element, and hence the valency of lead in this particular compound has been mentioned, lead 2 oxalate. So the valency of lead is 2, oxalate, that also 2, same valency, cancels out each other, so PbC2O4. Chromium phosphate, or we can also write chromium 3 phosphate, CrPO4. Chromium 3 phosphate, CrPO4 phosphate, valency 3, chromium valency 3, cancels out each other. Platinous chromate. Remember in the previous lecture I told you the lower valencies are termed as us. This suffix is added. Platinum to platinus. Platinus or platinum 2, same thing. Lead 2 or plumbus, same thing. Copper 2 or cuprous, same thing. So this us is related to the lower valencies. So platinus, chromate, so platinum, valency 2, chromate, CrO4, it's already having valency 2. So that same valency cancels out each other. Platinus, chromate, Pt, CrO4. Magnesium perchlorate, MgClO4 whole twice. Magnesium perchlorate, magnesium valency 2, perchlorate, ClO4, valency 1. Zinc carbide, zinc valency 2, and carbide valency 4. So Zn4, C2 cross multiply. Arsenic sulfide, As2S3, arsenic valency 3, and sulfur, that's sulfide valency 2. Manganese hypochlorite, that's valency manganese hypochlorite, MnClO whole twice. MnClO whole twice. Okay? Manganese 2 and hypochlorite valency 1. And lithium thiosulfate, Li2S2O3, similar to sodium thiosulfate, Na2S2O3. The lithium thiosulfate, Li2S2O3. Okay? All right. Now, you may say in your book it's having a big list of table, or the list is there about formulas. A table is there so about molecular formulas. A list is given over there. You may find these formulas over there, or you may not find these formulas over there. If you do not find this formula, there is no way of thinking or telling it is out of the book or it is beyond the syllabus. I'll absolutely reject that one, because all these formulas are directly from your book. If there is not in the list, doesn't matter. But if you're having, but it's there in the book, and where it's there, I'll discuss in the later. Coming to the next question of the classwork, that's percentage of potassium present in potassium ferrocyanide. What is potassium ferrocyanide? Previously I told you K4 FeCN6. Now we will calculate the percentage of potassium in potassium ferrocyanide. We know that the potassium atomic mass 39, iron 56, carbon 12, and nitrogen 14. And we get as 368 AMU. And I said previously also, and you can watch it and you can see each and every calculation. I'm writing this AMUs so that I do not miss it. If you practice like this way, it will automatically become your habit of writing these units just beside the integers, and you will never miss these units. If you're having this practice, your habit of writing the units, it will be your habit. So you will never miss the units. All right. So 368 AMU is the molecular mass of potassium ferrocyanide, and units are, as I written, that units are compulsory when you are calculating the molecular mass of or any compound. Units are compulsory. I repeat, and I'm saying it loudly because it is very, very important. Do not miss the units. Units are very, very important. Units are compulsory to write. Okay. So percentage of potassium, that becomes 42.39%. 156 AMU by 368 AMU, that gives 42.39%. Now, how to remember hundreds of chemical formulas? Many students ask me this question, sir, how can we remember so many formulas? It's so difficult. I will always say it's not so difficult. You don't have to remember. How you can remember? There is a very simple trick to remember hundreds and hundreds of formulas. It's a very, very, very simple trick is there. You don't have to remember so many hundreds of formulas. You just have to remember only few things. What are the things? The first, there is a table. The list is given over there. In your book, class 9 if you're having, and if you're not having, the materials are already, you're having the study material, the chapters I have provided to you of the first chapter, the pages. Now, from those you can check it out that there is a list of basic radicals, a table. There is a list of acid radicals given, and along with that, the valencies are also given. So the symbols of the elements or the symbols of the cations, the symbols of the anions, the element's name, and their valencies. So element or the cations and their valencies, anions and their valencies. And if you calculate, you just have to remember almost probably there are 23 cations and probably 29, 30, 31, 32 anions. If you can remember only these 55, or rather let's consider exactly maximum of 60, maximum, let me tell you. If you remember, if you calculate, almost there are 23 or there are 32 probably. Exact figures I don't remember right now. So if you can remember these numbers together, cations and anions together and their valencies, then just you have to do cross multiplication and combination, nothing else. For example, let's think you can practice on your own. Let me tell you the trick. You can practice on your own. You go through the table. The first element you will find. Let's consider the first element is sodium. Let us consider the first element is sodium. So what can I write? You're having the anion list. sodium chloride, sodium nitrate, sodium sulfate, sodium bisulfite, sodium thisulfate, sodium nitrate, sodium nitrate, sodium phosphate. You will just cross multiply, nothing else you have to do. You will just cross multiply these things, right? You will just cross multiply the valencies, and you're having the symbols with you, and you will see that with one cation you're having almost 30 compounds, so many. And the symbols you're having with you, 30 compounds. Repeat the same thing with the second cation, 30. And when it will be over, you will see you are having a list of almost 700 formulas. So do you think that you have to remember 700 formulas? I don't think so. I really don't think so. You just have to remember few, almost 23 cations, 23 cations, and almost 31 anions. And if you remember these cation symbols and their valencies, that's all. Almost 650 formulas you will be able to remember. That's the guarantee I can give you. Simple, nothing else. You have to practice. The next, coming to empirical formulas, the classwork, empirical formulas. Few compounds are given: hexane, acetone, acetic acid, urea, Freon 12. Hexane. Empirical formulas in the previous lecture also, only I told you, that's the simplest molecular formula. The simplest molecular formula which represents the ratio in which every atom are present in that particular formula. That means the molecular formula reduced to its lowest possible atomic ratio. That's all. For example, hexane. What is hexane? C6H6. C6H6. What's common? 6. So if you reduce this one to the lowest possible atomic ratio, it will become CH, 1:1. 1:1. Hexane C6H6. Sorry, I made a mistake over there. It's not be hexane. Hexane is not C6H6. It will be benzene. I'm very sorry, dear. I'm very sorry. C6H6 is not hexane. It's benzene is C6. Now coming to the next empirical formulas. There's a list given: hexane. Sorry, I made a typing mistake over there. It will be benzene. Next question, empirical formulas. A list given: benzene, you can see, acetone, acetic acid, urea, Freon 12. As I said, empirical formula, that was, the discussion was done in the previous, that means reducing a formula to its lowest atomic ratio. That means in a compound or in a molecule, the lowest atomic ratio, I have to reduce that molecule into the lowest atomic ratio, right? Benzene, the formula is C6H6, the lowest possible is CH. How? Explain. Its common is 6. You can see 6 carbon atoms and 6 hydrogen atoms. What is common? That is 6. So the lowest atomic ratio in which the atoms are present in that particular molecule, that's the empirical formula, 1:1. And from here we can get the empirical formula CH, which represents that carbon and hydrogen are present as 1:1 in the ratio. Acetone, the formula CH3COCH3, this is acetone. The 3. Now when this type of formulas will come, reduce this one into, club all the atoms together, then you will be able to identify that whether you're having any integers or any common things over there or not. Okay, any common things over there or not. Club all the atom or all similar atoms together. Look, with the acetone, CH3COCH3, carbon, 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 different. So club all the carbons together. So 3 carbon atoms, 6 hydrogen atoms, and 1 oxygen atoms. So see, 3 carbon atoms, 6 hydrogen atom, and 1 oxygen atom. That gives that gives 3 carbon atom, 1 hydrogen atom, and 1 oxygen atom, and that gives C3H6O. Anything common? Nothing is common. So the empirical formula will be C3H6O. That's all. Nothing common. So the empirical formula and the molecular formula remains the same. Clear? With acetic acid, once again we will club is CH3COOH, C2H4O2. But here we are having one common. 2. If it 2 C2H4O2. So 2 is common. So CH2O. That's the empirical formula. The next compound, urea, NH2CONH2, N2H4CO. Common? No, nothing is common, because nitrogen 2, hydrogen 4, but carbon and oxygen, they are 1, 1. We cannot reduce it anything else, any lower to that. So urea is also having the same empirical formula as of the molecular formula. Freon 12. The molecular formula is CCl2F2. Nothing is common. So the molecular formula and the empirical formula remains the same. And that's all with this. We will be having now a homework given, exercise of chapter 1. The exercise will be provided to you, exercise of chapter 1, and practice the table, right? The table of variable valency is a table given in the study material section. Basic radicals and acid radicals given in your book. Write that table down in your exercise copies. All right. So if you're having any more queries, anything else, you can contact me, or Singh sir is there, anyone who are comfortable with. Okay, so thank you so much. That's all with the class for today. Thank you.